here we go. So now we're finally moving into our next learning target, 2.2. So those last 3 lessons, we're all just dealing with one learning target of solving systems of equations. And I taught you 4 different methods, okay? Now we're moving on to solving system of inequalities. Luckily for this, we're only going to have one method, okay? So that's why it's just 2.2. There's not like an A, B, or C, because there's just one lesson for this learning target. And then we're going to do a learning target 2.3 starting on Monday. So when thinking about what the solution is, and this is a key point that I've tried to emphasize earlier this year, is what is the solution to an equation, right? Or the solution to this graph or something like that, or an inequality. And that's a key thing. We're always trying to solve these equations. We're trying to find the solution. And typically the solution is whatever makes the original thing true. And so let's just summarize all the different things that we've been solving so far this year. First, we learned how to solve an equation. And when we solved an equation, what did our solution look like? What would we like box up? What would it be? Any ideas? Would it be like an animal or a color? A number, yeah. The solution would just be a number, right? Solving an equation, usually we would say like x equals 2, and that's our solution, right? 2 is the solution. If I plug the 2 back into the equation, it would make it true. Awesome. So that's what we started off with this year. Then we learned about some inequalities. What did the solution look like for an inequality? Was it also just a single number? No, it was a whole bunch of numbers, wasn't it? And we show that on a graph with an arrow going a certain direction. So an inequality, that was more than one number. It was a whole bunch of numbers. It was a range. We'd say, well, anything bigger than 2 is a solution here. Or anything less than 25. Any number less than or equal to 25. Those are all the solutions to this inequality, right? There's a whole bunch of answers, but they have to meet that certain condition. Then we got to these things called systems, which meant we have more than one. We just went over how to solve systems of equations. We learned a whole bunch of different methods. And what did the solution to a system of equations always look like? What was the final thing we boxed up? That coordinate, that ordered pair, right? Like an x and a y value. That one point, that one x and y combination that would make all the equations true. So the solution to a system of equations was an ordered pair. Again, one thing, one answer, one x and one y together. And now we're going to learn about a system of inequalities. Any guesses as to what we think the solution will look like for a system of inequalities based on this pattern that's been kind of going on here? I'm sorry, I just heard a bunch of mumbles. I'm sure they were correct. What'd you say? A range of ordered pairs. You said a line. So if this was one number and this was a range of numbers, then a system of equations is one ordered pair. Then the system of inequalities is going to be a whole range of ordered pairs. So it's going to be a whole bunch of points, but we're going to represent that with something called a feasible region. We're going to represent this on a graph, and we're going to shade it in. And that shaded region we call the feasible region. The word feasible means it's like attainable. It means that's where we go for the good stuff. And so it is going to essentially be a collection of ordered pairs. But again, we're not going to list every ordered pair. There's an infinite number of them. And so we just will represent this on our graph. Just like with the inequality, we would draw a line in one direction. Since it's a system of inequalities, we're going to have that coordinate plane. And we're going to have a whole shaded area of that coordinate plane that represents our solution. Okay, you don't need to jot all this down. This is more just talking points for you to kind of conceptualize and understand what we're doing. And so when we solve this system of inequalities, this solution can be just an infinite number of these ordered pairs. So it's a whole bunch of X and Y combinations, but we're not going to list every ordered pair. There's an infinite number. We can't list them all. And so to represent where all those X and Y combinations are, we highlight this area and we call it a feasible region, which we're just going to shade in, like with our pen or pencil or whatever. We're going to shade in this area and say, hey, this is where all the answers are. All these ordered pairs in this part of my graph, all these ordered pairs are where all the solutions are. And so the neat thing about this feasible region is then that any coordinate in that region, so I have this whole shaded area, pick any X and Y in there, plug that X and Y into that inequality, and it's going to make it true. It's going to make both those inequalities true. All right, so it's a whole bunch of these infinite ordered pairs. So again, don't worry about writing all this down. It is posted online later, but just want to kind of get you thinking about what we're doing here. All right, so just some reminders about graphing inequalities. So we're going to be graphing these now in 2 dimensions, meaning an X and a Y, as opposed to before we were graphing it just in 1 dimension on the number line. It's very similar. Whereas, look at these first 2 symbols. Those are both greater than or equal to symbols. And for both of them, since they're both greater than or equal to's, we will shade above those lines, because doesn't the word greater kind of mean up or higher or above you? Greater is on top. And so if you have a greater than or equals line, you're going to shade above them. Now the one difference is that or equals to piece. So see how this one has that line underneath. If there's a solid line underneath your inequality, then when I draw that line, I'm going to make it a solid line. And remember that or equals means that like a point on my line is part of the solution. This is kind of similar to drawing that circle and filling it in. Remember the closed circle that we had with just a single one-dimensional inequality? Whereas if there's no line underneath, if it's just this greater than symbol, we use a dashed line, which is similar to an open circle on the number line. So that dashed line means this is the edge of my region, but a point on this edge doesn't count. It doesn't work for my solution. You can't have a point on it. But every point up to it, if you get really, really close to it, those points all work, but not a point right on the line. That is not part of my solution. So we use a dashed line to show that there's like breaks in the line, to show that it's not actually this line, but it's really, really close to this line. The solid line means, yes, this is part of my solution. It could equal a point on this line. And then the less than, or the less than or equal to, you would shade below those, because when you think of something that's less, I think lower, below you, beneath. Less than is underneath the line on the graph. And so we'd color in that whole area. And then same thing, dashed line versus solid line. If it's got the solid or equals line underneath it, we do a solid line when we draw that on our graph, on our coordinate plane. All right, let's rock and roll. So what I would suggest doing before you actually just graph these 2 inequalities, remember we're going to graph both of them and then do some shading and see where the shading overlaps. We want to first ask ourselves, hey, what kind of a line are we going to have? Will it be a solid line or a dashed line? And then once we've got that line drawn, are we going to shade above this line or below the line? So look at this first inequality here. And all I really need to look at is that inequality symbol, and that's going to give me all the information I need for how to draw my line. So this is just a less than symbol. Will that be a solid line or a dashed line? Dashed line, because it does not have that or equals line underneath. And would I shade above this line or below this line? So I see that symbol. I think to me it looks like a capital L which stands for less than. So that's going to be lower, below this line. And then for this second one, that's a greater than or equal to symbol. Now this does have that or equal to, that solid line underneath it to show that it's equal to, so this will be a solid line. And it's a greater than symbol. Greater means above or on top of. This is, oops. So we are going to shade above this line. All right, so sometimes it really helps to write those two things out. I see many times on tests, kids will draw one line and then they'll write a note. They're like, oh, Wojcik, this was supposed to be dashed, or, oh, shaded the wrong area. You really don't want to shade the wrong area because it's hard to change all that on your graph. Okay, so let's graph these. They're both in slope-intercept form, so that should be easy for us to graph. Let's start with this first line. And when I'm graphing it, you can kind of think of it as just an equation, like y equals mx plus b, even though it's technically y is less than mx plus b, but the points on our line are still going to be represented the same way. So I'm going to start by plotting the y-intercept, which is the number by itself. That's a -2. So I'm going to go down 2 units on my y-axis. And then the slope, I look in front of the x and I see a -2 over 1, right? If there's not a fraction, I make it into a fraction by writing it over 1. And so that's where I move my pen, down 2, right 1. Down 2, right 1, down 2, right 1. And we just continue that pattern. To go in the other direction, I would go up 2, left 1, up 2, left 1, up 2, left 1. And there's our dots. So far, this is just like solving systems of equations by graphing that we did at the first half of today. But now is where the changes come in. Do not connect the dots yet. Because we have to think about what type of a line we're going to use to connect these dots. All right, we said that this is going to be a dashed line, since that inequality symbol is just a less than symbol. So when I connect these dots, I'm going to do this. I'm just going to kind of like piece it together. I'm not going to connect everything. I'm just representing it with a dashed line. However you want to show that, just make sure that there's gaps in that line somehow. And now we have the shading to do. This is a less than symbol, which means we will be shading below this line. So for above and below, everybody, if you look at this line, oftentimes students get confused with, well, do I shade to the right or to the left? Instead, you should be thinking up and down. So this is always vertical. It's always up and down, above and below, greater than, less than. This is less than, that's below. So to figure out, well, which part of this line is actually less than, it's more difficult the more like up and down a line is. But to keep it straight, go anywhere on your line. Put your pencil down on any point. And since this is less than, that means below. Below means down, doesn't it? So move your pen downward. And this is the area that you want to shade in. Okay, so everything here would all be shaded in. Now you don't have to go nuts with the coloring if you've got like pens or pencils or whatever. Just drawing lines like this is more than adequate. But if you want to really color it in, it's nice, especially if you have 2 different colored pencils, because then when we graph the other one and the colors overlap, it makes a new pretty color. That's pretty awesome if you pick the right combination. Okay, now we have to graph the second inequality. It's also already in slope-intercept form. I'm going to start by plotting the y-intercept of 3. So I'm going to move my pen from the origin, from 0, 0, go up 1, 2, 3, and put a dot. That's my starting point. That's where I begin. And the slope is the number in front of the x. So that's a 1/2. Rise over run means up 1, right 2, up 1, right 2. So here we go, up 1, right 2, up 1, right 2. I can go backwards by flipping both of those, by going down 1, left 2, down 1, left 2. You should have a bunch of points all in a row. Now we need to draw the line, but is this going to be a solid line or a dashed line? It's solid, good, because it's got that or equals line underneath it. So I'm going to draw a solid line connecting all these dots. And then shading. This is a greater than symbol, which means we shade above it. So from any point on that line, pick a point, and above, greater than means up, so move up. That means this whole area of my graph is going to get shaded in. So I'm going to shade in this whole region. On my graph. Now, if you did your shading correctly, there should be 4 different distinct areas of shading on your coordinate plane. There's one area that has no shading at all. One area has just one color. Another area has just the other color. And one area has both. Do you see that? How like from where they crisscross, it makes like an X, and there's 4 different sections. Our solution is going to be the area that has both shading, the shading from both of those inequalities. And so I am just going to draw a little highlighter here to show you that it's this entire region is my solution. So once you get that, I recommend maybe making it extra dark. Like if you want to do your first 2 areas kind of really lightly shaded, and then kind of really darken in, or at least highlight or darken that outside barrier to show me that you know where the solution area is, where this feasible region is located. So for me, it's every point inside of here is a solution to that system of inequalities. Now, going back to the solution is the values that make the original problems true. And we said for a system of inequalities, it's this feasible region, or it's a whole range of ordered pairs. So here's what's pretty cool. I can take any point inside of that double shaded region, and whatever that coordinate is, so like this point here is -10, 0, and that's in my feasible region. So if I plug -10 in for x and 0 in for y, it should be true in both of those problems. Right? So if y is a 0 and x is a -10, this would give me 20 minus 2, which equals 18. Is 0 less than 18, everybody? For sure it is. So it works for that first inequality, that 1 point. Does it work for the second one? Well, y is a 0. X is -10. All right, -10 times 1/2 is -5. Plus 3 is -2. So is 0 greater than or equal to -2? Is that a true statement also? For sure, it is. So that one ordered pair, this point -10, 0, it works for both of those inequalities. So it is a solution, not the solution. But the cool thing is I could take any point anywhere in this feasible region and it would work for both of those inequalities. I could even take a point on this line down here, on, in my case, this bluish black line, and that would work. But a point on my green line would not work. Okay, because that's a dashed line. I can't use a point on the dashed line, but I can use a point on the solid line. And also it's important to know that just because my coordinate plane ends right here doesn't mean that's the only points that make the solution. Remember, this coordinate plane goes on forever out in the direction. So this would still go way out. So any point, way out there and up there and over there, like you've got tons of additional points that would still make these inequalities true. It's an infinite region, goes on forever. All right, not too different from the graphing equations that we did at the beginning of class, right? Is that pretty similar? You just have these two new pieces. That should be pretty simple. Is it solid line or dash line? And do you shade above it or shade below it? And then the other different thing is for writing our final solution, I'm not going to write an ordered pair. Your actual solution, like the final thing that you would box up like on a test, is just this shaded area. So just make sure that that's really extra highlighted or darkened, or there's some way that you can make sure that I know, oh, this is definitely the solution area. This is definitely that feasible region. All right, I want you to try this one on your own right now. So y is greater than -3. So graph that. Remember, that's going to be just a horizontal line because it only has a y value. But then you have to determine, will it be a solid line or dash line? And do you shade above it or shade below it? And then the second one, y is less than or equal to -5/3 x plus 2. So go ahead and graph both of those on the same coordinate plane. Do your shading and find out where both of those overlap. Awesome. Make sure you use the solid line or the dash line. You shade in the right spot. Looks good. You dropped your graph paper. Nice. Isn't coloring fun? Yay. And then just make sure that overlapping region is either darkened in more or a distinct different color, or you really kind of sharpen those edges of that region, just like I did with the highlighter on mine. You don't need to use a highlighter, but some way to indicate that this one part of my graph is our solution. All right, so y greater than -3. Since it's just a y, I'm going to go down to -3, 1, 2, 3 on the y-axis and put a dot. And I will draw in a horizontal line. But one thing, this is just a greater than symbol. It's not or equals to. So I have to do a dash line. Okay, so make a horizontal dash line right through this -3. And then it says greater than means above. So I'm going to shade above this line. So however you want to show that, I mean, even just shading like this, up and down. That's kind of like a guide for you to realize, oh, this is the part of my graph that I shade. The second one, y is less than or equal to -5/3 x plus 2. I look at that plus 2, and I plot that point first on my y-axis, up 2. My slope is -5/3. All right, so it's negative. That means I'm going to move down 5 and then right 3 instead of up 5 and right 3. Make sure you're still moving to the right, whatever that denominator is. So from here I go down 1, 2, 3, 4, 5, and right 1, 2, 3, put a dot. 1, 2, 3, 4, 5, 1, 2, 3, put a dot. I can also go backwards for both of those directions. Up 1, 2, 3, 4, 5, left 1, 2, 3. So those are my points for my line, my guide. But now will it be a solid line or a dashed line? And if I look at that inequality symbol, I see it's got that or equals to solid line underneath it. So we do draw a solid line to connect these dots. It's a less than symbol. So less means below, underneath it. So underneath this line would be this entire region here. So that's the less than area. And then look for the double shading. Where do I have both of my colors, the red and the blue shading? And so that's right here. Right there. So everything inside that highlight would be my feasible region. Any point, any ordered pair inside of there would be a solution to this system of inequalities. All right, quick check around the room. Everyone, can you give me a thumb up, thumb down, and a thumb to the side based on how you're feeling with this? We pretty good? We terrible? Or we like, maybe a little bit more practice?
How is the bottom problem going down?
Like the shading?
Yeah.
So this is a less than symbol. Looks like an L, right? That's a less than. And so if I look at, let me use a different color. So this is that line. And so you're asking, like, how do I know where to shade, which part? So less than means down, below. And so if I go to any point on this line, if you move your pen downwards, that's this area. So from any point, if I go down, down, it's always going to be on this side. So just think vertically, up and down, instead of thinking left and right. Yep, I would have shaded this area, and my feasible region would have been this upper right-hand corner instead.